Good morning, everybody. Just message me in the chat to make sure that you all are hearing me, please. All right. So cool. You all are hearing me, right? So for those students who out there in Trinidad and the Caribbean who are interested in joining my class, this is the information you need to know. This is my email address, terrysdavid@gmail.com. You can send me a WhatsApp at 784-2059, right? Considering information about joining the class. All right. So this particular session here, it's being streamed as a sample for those who are not in my class, right? So continuing from where we left off last week, we were doing the June 2012 paper, and we were on question 5. So let's continue with this paper. All right. Question 5 says state the equation for the general gas law. All right. Now, we basically have 3 gas laws. We have Charles' law, we have Boyle's law, and the pressure law. Now, each of these laws can be combined to form one general law, right, which you call the general gas law, and it's written like this. It is P1 V1 over T1, which is equal to P2 V2 over T2, right? That is the formula for the general gas law. Well, what you should do with this question, you're going to need to state what each of these terms mean. So P1 is my initial pressure. One second, just give me a second. One sec. Just need to answer this. Yeah, sorry about that, right? Okay, so like I said, you need to state what each of these terms mean. So P1 is my initial pressure, right? P2 is my final pressure. V1 is initial volume. V2 is final volume, right? And again, you need to state what T1 and T2 are, right? So T1 is initial temperature. T2 is final temperature, right? Now, I want you all to remember and keep this in mind. the temperature has to be in Kelvin. All right. I've seen where students, when they get questions pertaining to the gas laws, the examiners give the question and they give the question in degrees Celsius, and students go and work the question and they get a question wrong because they didn't convert to Kelvin. So please remember, when we are using the gas laws, temperature must be in Kelvin, right? So keep that in mind. Now, let's continue now. So a little girl blew up a balloon during a Christmas celebration. Explain in terms of the kinetic theory how pressure is exerted by the air in the balloon. All right. So basically what we have here, we have, let's say there's a balloon, we have particles of air, right? Because this is what the kinetic theory is about. Everything is made up of particles. Now, we want to explain how pressure is exerted by the air in the balloon, right? And we're going to use the kinetic theory to do this. Now, please, when you are answering questions, you need to be crystal clear about what you are saying, right? It's not about old talking, it's about saying exactly what is required. So the kinetic theory is basically saying that everything is made up of particles, right? So everything is made up of particles, right? Now, this is what we need to say to get the marks here. So the air particles, right? Because remember you're blowing up the balloon, so the air particles are moving randomly in all directions, right? So air particles moving randomly in all directions. They collide with the walls of the container. Well, in this case, the walls of the balloon, right? So they collide with the walls of the balloon. Now, these particles, right, they undergo a change in momentum, right? Now, let me show you why. So if you have, let's say this was an air particle here, right? And this here, let me use a different color here. So this is the inner walls of the balloon, right? Now, what is going to happen here is that particle is going to move here. Let's say the mass is m and the velocity is v. When it hits the wall of the balloon, it's going to rebound and then it's going to do this, right? And it's going to have a new velocity v, right? So what has happened is that it has a change in velocity, therefore a change in momentum, right? Now remember, according to Newton's second law of motion, force is proportional to the rate of change of momentum. So therefore, since these particles undergo a change in momentum, they exert, so the particles exert a force on the wall of the balloon, right? So they exert a force. And we also know that pressure is equal to force over area, right? So this force that the particles are exerting on the walls of the container, it exerts a pressure, all right? So you have to try to be clear about what you're saying here. So basically, this is what is required. the particles of air inside the balloon, they're continuously moving randomly in all directions, right? They collide with the walls of the inner walls of the balloon. Because they collide with the inner walls of the balloon, they undergo a change in momentum, which means that they exert a force on the inner wall of the balloon. And because they're exerting a force over a particular area, they exert a pressure on the inside of the balloon. All right? So try to be logical in terms of how you're explaining this answer. All right? So moving on. So this is part B here. So you have a block of ice that has a mass of 2,000 grams. It was heated from 0 to steam at 100 degrees Celsius. And it wants us to calculate the energy in joules, right? So remember what I told you all in class. Visually, we need to see what's happening here. So we started off with a block of ice, which was heated from 0 degrees to steam. So we started off with ice. So this is ice, right? And so they told you that it starts at 0 degrees. So this is 0 degrees Celsius. Now this ice must first be converted into water at 0 degrees Celsius, right? Then when the water is converted, when the water is at 0 degrees, it has to be converted, or it first has to go to water at 100 degrees, right? And then the last part is to convert this into steam at 100 degrees Celsius. All right? So visually, what you all should do is to draw a diagram like this, so you know what each of the arrow represents. All right? So the mass is this, and they've given us information about the latent heat of vaporization for steam, latent heat of fusion for ice, and the specific heat capacity of water, right? So I'll give you all a few minutes to give me an answer for this, right? So use your calculator and try to work out this for me, please. All right, so I'll give you all a few minutes. I'll just mute my mic for a second. All right, so I'm seeing that Emily got how much is that she got there? 6 million joules, right? So let me see if that is correct. All right. So in order to work these questions where we're heating up something, you all need to draw a diagram because you need to understand clearly in your mind what we are actually working out, right? Now in class, I gave you all a heating curve and I showed you all at each section which formula we're supposed to use. So the first thing, you have ice at 0 degrees. The first thing you need to do is to convert that into water at 0 degrees, right? So the formula we're going to use for this phase or this stage here is E equal mLF. That's the latent heat of fusion. We are not changing temperature, all we are doing is changing state. Then when we have water at 0 degrees, and so when we have water here and here, the formula we're going to use here, because we only change in temperature, is MC delta theta. And then in this stage here, we're gonna be converting steam at 100 degrees into, water at 100 into steam at 100. So for this one, we have a change of state without a change in temperature. So that is MLV, right? So we have to work this out in 3 parts basically. So the first part, equal MLF, right? Now, the mass of the block of ice is 2000 grams. So basically 2000 grams is actually 2 kilograms, right? So the reason why they gave you it like that, they want to make sure you know how to convert between grams and kilograms. So 2000, let's write this on the side here. So 2000 grams is the same as 2 kilograms. Right? Because to convert grams into kilogram, we need to divide by 1000. So this is 2 multiplied by latent heat of fusion of ice is, they give us it as 330,123. Right? Let's get my calculator here. So that is, right, so don't need a calculator for that. 660,123 joules. So that's for the first phase, right? The next one now is E equal mc delta theta, in which case the mass is 2 kg, again, multiplied by C. They've given us C as 4200, 4200, multiplied by my change in temperature. My change in temperature, remember I am starting off with water at 0 and I'm converting into steam at 0. So that's really 100 minus 0, which is 100. So this will give me 2 multiplied by 4200 multiplied by 100, and that will give me 840,000. Right? So this is 840,123 joules. So that is second section. And then E equal mLV, which is 2 multiplied by the latent heat of vaporization, which is this number here. So that is 2,250,000. Now y'all could work in standard form, right, if you want. So 2 multiplied by 2,250,123, and that'll give me 4 million. So this is 4,500,123 joules, right? So I booked out the energy for the 3 sections, and the question is asking for the energy to do that whole conversion. So therefore, my total energy is equal to 660,123 plus 840,123 plus 4,500,000, and that'll give me, so that's 840,123 plus 660,123. Right, and this will give us 6,123,123. So basically 6 million joules, right? Now you can give your answer in standard form, right, if you want. So that will be 6 by 10 to the 6 joules, right? So you can give your answers that's fine. If they had asked you to give your answer in megajoules, then it'll be 6 megajoules. All right. So let me just check and make sure anybody. All right. So I saw Tyrese got the same thing too. All right. Yes, Xavier, morning. I know some of you all are a little comfy being at home. You know, you just roll off your bed and come to class. All right. So that was number 5. What else we have here? So they want us in this next part. They said if the activity in B1 took place in 6,000 seconds, how much power is utilized, right? Now, you all need to know this formula. Power is energy over time, right? Power is the rate at which work is being done. So you just worked out the amount of heat there, or energy required, and that was 1, 2, 3. Basically, we got 6 million joules, right? And we're just going to take that answer and divide by 6,000, right? And basically, when you divide that, you're going to get 1,000 watts, right? So the power, how much power is utilized? So 1,000 watts is utilized, right? And as I indicated previously in class, you need to state the formula, you need to substitute, and you need to get the answer, right? So typical calculation will be 3 marks. So you might get 1 mark for this, 1 mark for substitution, and 1 mark for this. And sometimes if they give you 4 marks for the calculation, what they're looking for is a unit. You need to specify the unit, right? Which in this case is watts. All right, is that the last question? Nope, we have a number 6. All right, so let's move on to number 6. So in this question here, they said electromagnetic waves have many properties, right? Write a paragraph describing at least 3 properties of electromagnetic waves. All right, so you all need to know what are the properties of electromagnetic waves, right? So I'm going to ask you all to give me some properties of electromagnetic waves, right? So we have several of them, so let me see what you all can come up with. All right, Kendall say they can travel through a vacuum. That's one. They obey the wave formula. That's true. Tyree saying and John saying they're transverse wave. That is true. Let me just double check something with this. Make sure I'm giving you the correct people opening, right? But continue giving me properties of EM waves. Oh, I just realized. Okay, I missed out a part one, right? But I'll go back to that just now. Alright, so Emily is saying that they can be diffracted, refracted, reflected, and interference occurs. Alright, so all of those are correct. Alright. So basically they want three properties. So we can say they can travel through a vacuum, right? Because we have light waves coming from the sun to the earth, and there's a vacuum between us and the earth, right? So they can travel through a vacuum. They all travel at the same speed, which is 3 by 10 to the 8 meters per second squared, right? Like you all said, they are transverse. Right? You all said they can be reflected, it can be diffracted, right? They can be reflected, diffracted, show interference. Right, so basically they just want any three properties, right, for 3 marks. And also, because they are transverse waves, they can be polarized, right? Now that is more at the cape level, but if you state it here, they won't penalize you. It's correct. So I missed out part 1 of the question, right, which is outline 3 differences between light waves and sound waves. So let me give you all a chance to answer this one. So what are 3 differences between light and sound? Alright, so John is saying light waves are transverse while sound is longitudinal. That is correct. Tyree saying that Light travels at 3 by 10 to the 8, sound at 340, right? Right. Xavier is saying about longitudinal and transverse, that's true. Kendall, light travels through a vacuum while sound needs a medium. Yep, that is true. Right? So you have several differences between light waves and sound waves. Emily saying light waves comprise of rays and particles, whereas sound waves comprise of compressions and refractions. Tyrese, light has a very short wavelength. Alright, so you'll kind of have a good idea as to what are the differences. So the first one is that the most obvious one and the one that they want for sure, light waves are transverse. Right, so light waves are transverse, whereas sound waves are longitudinal. Right, so that's my first difference. Second thing is light waves can travel through a vacuum. Right, because it's an electromagnetic wave. It doesn't require material. But in the case of sound waves now, a material medium is required. Right, so sound waves cannot travel through a vacuum. It needs a material medium in order to travel. Right, so I've seen them ask questions where you had to describe an experiment to show this. An experiment to show this is the bell jar experiment, where we have a bell inside an enclosed jar, and if we remove, so you have the bell ringing, and as you slowly remove the air from this bell jar, you're going to stop hearing the sound, right? And that experiment shows that a material medium is required in order for sound waves to travel, right? Our next difference, like you all said, the speed of light is actually 3 by 10 to the 8 meters per second, right, in air, right? And the speed of sound is much smaller. It's around 340 meters per second, right? And this is in air, all right? So the speed is different, vastly different. Also the wavelength, you can also speak about the wavelength. Light has a very short wavelength as compared to sound. So we could also talk about the wavelength. So very short wavelength. Right, and where sound much larger than light, right? So much larger wavelength, right? So any three differences, and that's essentially what they want. So let's go back to this one here now. So Carl and his friend Tommy were doing a SBA on estimating the speed of sound in air using an echo method, right? Carl stands 100 meters from the wall. Carl claps 2 wooden blocks to produce a series of echoes, and Tommy, who is standing beside him, starts a stopwatch. After one echo, Tommy stops the watch. The process is repeated, and the time for 50 echoes was calculated at 30.3 seconds. Calculate the speed of the sound generated. Now, see why it's a good idea to know the order of magnitude of certain things. So we know that the speed of sound should be around 340 or sometimes 330, 340 meters per second, right? So we know that. Now, even if you're unsure about how to do the calculation, you know this is the answer you're looking for, something around there. Now, you have 50 echoes, right? And the time taken for those 50 echoes is 30.3 seconds. So what we need to do, we need to find the time for one echo basically, right? So that's what we're going to do first. So we need to find the time for one echo, right? Which is, we need to take the 30.3 and divide by 50, right? Because 50 echoes in total. So 30.3 divided by 50. That'll give me 0.606 seconds, right? So that is essentially the time taken for an echo to take place. Now, with these experiments, right, so they could actually in the exam to describe an experiment to estimate the speed of sound in air, right? This is the experiment they're looking for. Now, think about it. When you hit the wooden block, you're going to produce a sound wave. But that sound wave is going to travel from where the block is, that's from here, right? Diagram drawn a little strange, right? So the sound wave is going to travel towards the wall. So it's going to travel a total distance of 100 meters to reach the wall. It's going to hit the wall and then it's going to be reflected and it's going to come back here, right? So the wave is going to travel an additional 100 meters. So therefore, the speed of the sound will be my total distance, which is 100 to go, hit the wall, and 100 to come back. So that's 100 plus an x 100 divided by my time, which is 0.606, right? Which is really 200 over 0.606. So that'll give us 200 divided by 0.606, and that'll give us 330 meters per second. So you notice we got the answer. So if you had known this fact before, right? If you had known this before, then you know that's what you're looking for, right? I just forgot to write that speed is really distance over time, right? That's the formula we're using. Speed is distance traveled over time taken, right? So that is question 6, part B. And I think this is the last part, yeah. All right, so a popular radio station broadcasts at a frequency of 100 by 10 to the 6 hertz. Calculate in centimeters the wavelength of the sound that is generated. All right. So essentially what they're asking us here is to use the wave formula, right? The wave formula is this: V is equal to F lambda, right? That's the wave formula. Now, they've given us a frequency and they want us to calculate wavelength, right? So wavelength, symbol for wavelength is lambda. So lambda is equal to V over F. The speed of an electromagnetic wave is this: 3 by 10 to the 8 meters per second. So it's 3.0 by 10 to the 8 meters per second over my frequency. My frequency, when I'm using the formula, has to be in hertz. So it's 100 multiplied by 10 to the 6. So let's work that out. So that's 3 by 10 to the 8 divided by 100 by 10 to the 6. And you're going to get 3 meters. Right? So you're going to get 3 meters. But the question asks us to give our answers in centimeters. So to convert meters to centimeters, we need to multiply by 100. So therefore, this is actually equal to 300 centimeters, right? So the answer is this: 300 centimeters, right? So are we all okay there? That is it for the June 2012 paper. Alright, so that's the June 2012 paper, right? So I'm gonna move on to another paper here. Alright, so I'm gonna move on to the June 2011 paper. Alright, so I'll give you all 2 minutes to make sure you're on to that paper right now. All right, so let's jump to the June 2011 paper, right? All right, so let's look at this paper here. So a taxi driver was taking his friend to a popular 2020 cricket match. Table 1 shows the vehicle's velocity for the first minute of the journey. All right, so we have velocity, and we have time in seconds. They want us to plot a graph of velocity versus time, right? Now, if you all are doing physics, you all need to be able to plot graphs properly, right? Because your first question, more than likely, is going to be a question where you have to plot a graph, right? So they want us to plot a graph of velocity versus time. Now, please make sure you understand what that means. Velocity versus time means that we're going to put velocity here. So velocity has to be on the y-axis, and time has to be here, right? I've seen where students, they mix up what they have to plot. Once we say plotting something versus something, the versus part, right, has to go on the x-axis. They can also tell you plot velocity against time, which means the same thing. All right, so basically we're going to plot the data. So I've done this for you. So this is what a graph is supposed to look like. All right, so you're going to have to practice plotting it on the graph paper that's in the exam. So we have velocity on the vertical axis, and we have time on the horizontal axis. So what you need to do, you're going to plot each of the points, and you're going to draw a line of best fit, right? If we look at the data, most of the points, they're all roughly line on the same straight line. All right, so that's basically it. You're gonna have to do this. Actually plot. You can go back to my graph and double check, but this is what it's supposed to look like. Now let's go on to part B. So in part B now, they're saying from the graph calculate the slope P. So most of the questions or the first question on your paper, you're gonna have to find, if it's a straight line, you're gonna have to find the slope, right? Now some things I need you all to remember here. When you are finding the slope, please do not use any points that you have plotted, right? Because when you plot data, that is experimental data. That is data you collected when you did the experiment. When you draw a line of best fit, what you are doing, that averages out all your data. So that line represents a combination of all your experimental results. So when you are trying to find the slope, if you use one of the points that you plotted, you are defeating the purpose, right? So what I've done, I've just drawn a triangle here. So I'm going to use 2 points on the line in order to find the slope, but I'm going to use 2 points that I have not used in the plot. So I'm going to use this point here, and I'm going to use this point here. Now the hardest thing for you all is to be able to write down what those 2 points are, right? So let's say I'm going to call this point A, and I'm going to call this point here, I'm going to call that B, right? What you all need to do, first thing you need to do is to write down the coordinates of A and the coordinates of B. So let's look at A. According to my scale, now remember you all going to have to plot the graph. So this will be 10, 12. So it's every 2. So that is, so the point A is 12. And this is what? This is 14. So A is 12, 14, and B is 54.62, right? So obviously your A and your B is going to be different to what I have, right? Now, in class, I told you all when you want to use the formula to find slope, once you write down the two coordinates, please label them. So this is x1, y1, and this here is x2, y2. And my slope, the formula for slope or gradient, right? So my slope, in this case I call it P, is equal to y2 minus y1 over x2 minus x1, right? You'll need to find slope in CSEC maths, so you should know this formula, slope. All right, so now we have the formula y2 minus y1 over x2 minus x1. So since I've labeled my terms, there's no way I should get confused. So y2 will be 62 minus 14 over 54 minus 12. All right? So at this point, we can use our calculator to work this out. So that's 62 minus 14 divided by brackets 54 minus 12. Right, so I'm getting 1.14, right? 1.14, right? They did not ask us for any unit, so let's put 1.14, right? All right, so we know the slope. That's the answer there, 1.14. The next part, what quantity does the slope P represent, right? I've seen them ask this a lot. When you work out the gradient, they want you to find out or state what the gradient is really represented, right? So let me ask you all this. So what does the gradient represent? Alright, so John, Tyrese, Emily, you all are saying acceleration, right? That's correct. Now, when you have to figure out what the slope represents, we need to look at what's happening here. You need to look at what is my y-axis and what is my x-axis. So you have velocity. Now this is a velocity time graph. If you find the slope of a velocity time graph, what we are finding here is acceleration. So acceleration is correct, right? So P represents the acceleration. So if they had asked me for a unit, therefore the unit for this should be meters per second squared, right? Sometimes they ask you for the unit when you work out the slope. You need to look at your units on your axes in order to do that. Now, let's move on. So now they come and they say, for the next minute, the vehicle's velocity was constant. Then for the final minute, the vehicle decelerated uniformly to stop on reaching the stadium, right? So this is what they say. So we have V, and we had already plotted this here, right, up to this point. And this represented the first 60 seconds, right? They said the vehicle's velocity was constant for the next minute. So they said for the next minute, the velocity was constant. What that means is that the velocity didn't change, So therefore, sorry, this is not 60, this is 120. Right? So it's constant up until 120 seconds. And then they said in the final minute, which is the final 60 seconds, it decelerated uniformly. So it's going to do this, right? So this is really, let's erase this here. This is 120 seconds. And this here is 180 seconds, right? So there's a continuity velocity time graph on page 3 to show this information and use the graph to determine the total distance traveled. So I have plotted the graph. This is what the graph looks like, right? So we have our velocity time graph. The first linear section, this first piece here, is the first part we had drawn. The part on top here represents constant velocity, and then the sloping part is where the decelerated. So the question, now apart from drawing the graph, the question also said, use the information to determine the total distance traveled, right? So I'm going to leave the graph up for a sec, and I want you all to determine the total distance traveled. If you don't have the paper in front of you, the final velocity, or the velocity at the top, right, was 69 meters per second, right? So if the velocity was 69 meters per second, I want you all to work out the total distance traveled for the 180 seconds, right? So I'll give you a few minutes to work that out. Right, so I'll wait for you all to give me an answer. So we're calculating the total distance traveled. All right, I'm seeing Emily and Tyrese got 8280. All right, so let me look at it. So we want to calculate the total distance traveled here, right? Now you have two options. The total distance traveled is really area on the velocity time graph, right? So let me just go back to this here. So distance traveled, right? So you want the total distance traveled, right? This here I told you was 69. So the total distance traveled is really the area under this whole graph. This here, this whole area represents the total distance traveled, right? That is my total distance traveled. So you have two options. You can either break up the shape into, use a different color here. You can break up the shape into a triangle, right, as one. you can also break this up and get this piece here, which is a rectangle, and you can also find this here, which is another triangle, and you add up that, right? That's one way you can work it out. But if you all know the formula, this shape here is a trapezium, and the area of a trapezium is equal to a half the sum of the parallel sides multiplied by each, right? But some people, they can't remember that formula, so what I will do, I'll work it out in steps, right? So let's call this A1, let's call this A2, and let's call this A3. So A1, right, let's work in baby steps here. Area of a triangle is a half base by height, so a half multiplied by 60, which is my base, multiplied by my height, which is 69, right? And this will give me as 0.5 multiplied by 60 multiplied by 69, and you're going to get 2070 meters, right? Then we can work out A2, which is rectangle. Area of the rectangle is base by height, right? Or length by width, length by breadth. So the base is 60 multiplied by my height, which is 69. So that is 60 multiplied by 69. You're going to get 4140 meters. And then the last part, A3, we have another triangle, which is a half multiplied by my base, which is 60, multiplied by my height, which is 69, right? Which is the same 2070. All right. So therefore my total distance now, so total distance travel is equal to A1 plus A2 plus A3, right? Which is, we're going to add up all of them. I'm not going to write it over. So that is 4140 plus 2070 plus 2070. And you're going to get 8280, right? Which is what you all are getting. 8280 meters. All right, so this represents my total distance travel, 8,280 meters. All right. Right, so the next thing they want the average velocity of the taxi to complete the journey. So average velocity is equal to total distance travel. So average velocity is total distance travel over total time taken. Right, my total distance travel, we just worked that out, we got 8280. So this is 8280 divided by my total time. We need to go back to the graph. My total time, if you look at it, the journey was actually 3 minutes. So my total time is 180 seconds. So this is 180. So 8280 divided by 180, and I'm going to get 46 meters per second because we're dealing with average velocity, right? So my average speed, or what is the speed x or average velocity? Right, average velocity, yeah. So average velocity is 46 meters per second. All right. So you all need to remember this formula here. This formula is average velocity. Average velocity is total distance traveled over total time taken, right? Make sure anybody, very good. Now the last part, they said if the total mass of the loaded taxi is 1500 kg, determine the momentum of the vehicle when it is traveling at constant velocity. So I'll give you all 2 minutes to please work that out for me. what is the momentum of the vehicle when it's traveling at constant velocity? All right, so let's see, somebody put P equal mv. All right, so you all need to know the formula for momentum. Right, please note it's momentum and not moment. Right, this is something that some students they confuse. So momentum, the formula for momentum is P is equal to m multiplied by v. Right, it's a formula you need to know. The mass in this case, they gave us the total mass. The total mass is 1500 kg multiplied by my velocity. Right, they said when the velocity was constant. So you're going back to your graph. Your velocity was constant, and that was constant at a value of 69 meters per second. Right, so this is 69 meters per second. So it's 1500 by 69. So 1500 multiplied by 69. Right, and you're gonna get 103,500. And because I'm multiplying mass by velocity, my unit for momentum is kg ms to the minus 1. Alright, so this is the momentum of the vehicle when it's traveling at constant velocity. So it's just a formula, P equal mv, and that's it. Do you have any more parts to the question? Oh, okay, so that's all I just worked over there. Oh, so we still have our next part to do. That's part E. They want us to define the term displacement. Can somebody tell me what is displacement? Joshua is saying displacement is the rate of change of velocity per unit time. No, that's not what displacement is. Tyrese is saying distance moving in a stated direction from equilibrium. Alright, you're kind of partly correct there. So, what displacement is, right? So, displacement is the distance moved in a particular direction, right? That's all they're looking for here. Right? So displacement is the distance moved in a particular direction. So you need to know the difference between distance and displacement. Right? Distance is a scalar quantity and displacement is a vector quantity. Right? But both of them are measured in meters. The best example or the easiest example for me to give you when you're in class, remember I gave you all this example. Let's say you have somebody playing football and they start at the point A during the game and then they do all of this. They run around the field, all of this, and they end up back at the point B. Right? You see all that squiggly that I just drew here? This here represents my distance. Right? That's the actual distance traveled. Right? That's a scalar quantity. However, if I draw a line from A to B, right, that represents my displacement. So this here represents my displacement. All right. So there's a difference between distance and displacement. Displacement has a directional component, right? Because a scalar quantity only has magnitude, just as a number, whereas a vector quantity has both a magnitude and a direction. Okay, so based on what I just said here, displacement is a vector quantity. Acceleration, can somebody tell me if acceleration is scalar or vector? So Emily is saying it's a vector quantity. That is correct. Acceleration is a vector quantity. It's not a scalar quantity. All right. So let's move on to question 2. Question is saying complete table 3 by inserting the correct symbol and SI unit which relate to the quantity shown in the column. So they have two quantities, specific heat capacity, the symbol is small c, and what is a unit, right? So the unit in this case is, for specific heat capacity, is joule per kilogram per Kelvin, right? It can also be joule per kilogram per degree Celsius, right? But the SI unit is joule per kilogram per Kelvin, right? They want specific latent heat of vaporization, right? So it's latent heat, so it's going to be L, and it's vaporization, so we're going to put a little V here, right? So that's the symbol for latent heat of vaporization, LV. and the unit in this case is joule per kilogram. Alright? Now if you all can't remember how to work out a unit, you just need to make sure you know the formulas. So we know E equal mc delta theta, right? So therefore C is equal to E over m multiplied by delta theta. Alright? Now in terms of units now, energy is measured in joules, mass is kg, and temperature change is Kelvin. So therefore my unit is joule kg to the minus 1 Kelvin to the minus 1. Right? That's how we get in that unit there. Also for latent heat vaporization, the formula is E equal mLV. So LV, latent heat vaporization, is E over m. In terms of units now, energy is measured in joules and mass is measured in kg. So therefore, this will be joule kg to the minus 1, right? So that's how we get any units here. So the next question now is asking us about heat capacity of a substance. So it's asking us to define heat capacity. Can somebody tell me what is heat capacity? So Kendall is saying the amount of energy required to raise the temperature of a substance by 1 degree. That is absolutely correct. Alright. The question is not asking for specific heat capacity. It's asking for heat capacity. So the energy required to increase the temperature of a substance by 1 degree. Right? So it's the energy required to increase the temperature of a substance by 1 degree, which is different from specific heat capacity. Right? And heat capacity, the symbol for heat capacity, it's a big C. Right? The next part, write the equation which relates specific heat capacity to heat capacity. Right? Can you all give me what the formula is that relates heat capacity and specific heat capacity? Alright, so seeing Tyrese, John, you all say the correct thing. Big C equal MC, M's my small c. So the formula is big C, which is heat capacity, is equal to M multiplied by small c. So this is heat capacity, and this here is specific heat capacity. All right. Okay, so they've given us a calculation to perform here. So a busy housewife left 25 grams of ice. So it's 25 grams of ice in an open insulated container while she was answering her cell phone. When she returned, the ice at 0 degrees was converted into water at 3 degrees. Calculate the energy needed for the ice to totally melt and to reach its present temperature. Assume no heat losses, right? Okay, so like I said, with these questions, you draw a diagram to visually see what's happening. So you have 25 grams, right? And this is ice. And the ice, and they're telling us that the ice is at 0 degrees C, right? Then that ice needs to be converted into water. So this is water at 0 degrees C, right? That's my first step. And then that water now needs to be converted into water at 3.0 degrees Celsius, right? So this is water. So assuming no heat losses, calculate the energy needed for the ice to totally melt. So I want you all to work that out for me and give me an answer. All right, so let's see, I have an answer from Emily here, which is 8,815. Said say you got the same thing. Right, Xavier got the same thing as well. Okay, so just like we did with the previous question concerning heating of a substance. So the first thing we need to do is to melt the ice, right? Which is at 0 degrees. We need to melt the ice at 0 degrees. So we're going to be using equal MLF for this first one. And then we have water at 0 degrees. And we're going to raise the temperature to 3 degrees Celsius. So we're going to use E equal MC delta theta in this case here. So we're going to work out the first part, which is equal MLF. Equal MLF. Right? The mass of the ice is 25 grams. We need to look at see how they've given us our units. And the units have been given in terms of kg. So first thing you would do is to convert the 25 grams into kg. To do that, we need to divide by 1000. So this is 0.025 kilogram. Okay, so that's your first thing. So 0.025 multiplied by the latent heat of fusion of ice, which is 34000. Right, so in the exam they're going to give you these pieces of information. You don't have to learn it off. 0.025 multiplied by 340,123, and you're going to get 8,500 joules. Right, so that's for the first step. That's to just melt the ice. Now we need to raise the temperature of the melted ice to 3 degrees. The formula for that one will be equal MC delta theta, which is 0.025 multiplied by C for water, which is 4200, multiplied by my change in temperature. You're going from 0 to 3 degrees, so it's 3 minus 0. So this is 0.025 multiplied by 4200 multiplied by 3 equal 315 joules, right? So now my total energy, will be equal to the 8,500 plus 315, and this will give me 8815 joules. All right, so I can't remember how much marks they're given for this, right? Usually when they give you thermal physics calculations, it's worth some marks. So let's see something. Yeah, so just to work out that part of the question, so this part of the question is actually worth 6 marks. So this is worth 6 marks. Right? So please, with all these questions, try to draw a diagram. Once you draw the diagram, you could kind of figure out which formula you need to use, right? So 6 marks just for doing that. Oh, and this part now is very similar to the question we just did. They said if this melting and heating activity took place over 300 seconds, calculate the rate at which the ice was receiving the heat, right? So again, the rate at which ice was receiving the heat, right? What they're really asking you here is for power. So P is equal to E over T, right? Or W over T, doesn't matter. You just worked out the amount of energy that was required to do that. That is 8815. So this is 8815 divided by the time taken to do that, which is 300 seconds, right? So divide this by 300 and you're going to get 29.38. So 29.38, right? And we can either give our answer in watts or joule per second, it doesn't matter, right? So it's 29.38 joules per second or watts. All right. So let's move on to number 3. So number 3, we have shows a simple cell, figure shows a simple cell connected to a circuit, right? So this is a simple cell. They didn't label it for you, but this is a simple cell, right? So that is providing power to this circuit, right? That is providing power to the circuit, right? Just give me a second, this thing give me a little trouble. Alright, so back to what we have here, right? Yeah, so as I was saying, so we have a cell, and the first part of the question is saying how does the flow of the current within the cell differ from that of the copper wire? So you have, this is the cell here, so the cell is producing the electricity for the circuit, and we have the copper wires that actually we use to connect the circuit. Now they said how does the flow of the current within the simple cell differ from that of the copper wire? Alright? Can I get some answers from this? So the question wants to know what is the difference between what is happening in the cell and the copper wire. So how does the flow of the current within the simple cell differ from that of the copper wire? Right? John, Emily, Xavier, Saeed, Tyrese, what do you all think? Nobody has an idea? So let me ask you all this. In the copper wire, what is actually moving in the copper wire for an electric current to flow? So let's start with the easiest piece, the wire. What's happening in the wire? What do we have flowing in the wire? Alright, so I ain't getting anything from anybody. So how does the flow of the current, right? So current is essentially a flow of charge particles, right? So inside the copper wire, we have free mobile electrons. So in the wire, we have free mobile electrons flowing, right? That's what happened inside the wire. In the case of the cell, right, we have dilute sulfuric acid here. In order for the cell to actually work, what you're gonna have is you have ions, right? So you have positive and negative ions, not IRONS, IONS, moving. So this is the difference they want. So how does the flow of current within the simple cell differ from that of the copper wire? So in the copper wire, the current is flowing because you have free electrons moving within the wire. In the case of the simple cell, we have positive and negative ions moving, right? That's what they want for the answer, all right? So just remember that current is a flow of charge, and the flow of charge could be the movement of electrons or ions, doesn't matter. Now, the next part here, they said name the material used for the positive terminal of a dry cell, right? So this has nothing to do with the diagram we just did. So name the material used for the positive terminal of a dry cell. Now you all need to be able to draw a dry cell. So the dry cell looks something like this. And then we have this. Right? So the question is asking, what is the name of the material used for the positive terminal? This is my positive terminal here. What is the name of that? Can somebody tell me? Alright, so Tyrese is saying carbon rod. That is correct. So the positive terminal here, right, it's carbon, right? So the positive terminal, the material used to make the positive terminal is carbon. Now the negative terminal, which is this piece here, right, this here. So name the material used for the negative terminal of the dry cell. So this one is just carbon. What's the negative terminal called? What material? Now guys, remember we did this in class, so you should have the notes even if you can't remember. Alright, so Tyrese is saying zinc, that is correct. So the material used to make the negative electrode is zinc. So please make sure you all know how to draw a diagram of a dry cell and to be able to label it. So you have the carbon rod, you have zinc casing, then you have ammonium chloride paste as your electrolyte, right? So let's do part 4 now. In the circuit, if the current, so we're going back to the circuit now. So that part of the question had nothing to do with the circuit, but we're going back to the circuit, right? So according to this diagram now, they said if the current is steady at 0.1 amp, calculate the charge that goes through in 60 seconds. So can you all tell me what formula am I supposed to use there? Actually, just work that out for me. Don't give me the formula. Just work it out for me and let me see what answer I get. Calculate the charge that fluid. Alright, so I've seen Emily and Kendall got 6. Right? Let's see. So the formula we're going to use is Q equal I multiplied by T. Right? You'll need to know this formula. This is how we find charge. So in this case, the current is 0.1 multiplied by my time, which is 60 seconds. Right? Please note that time is measured in seconds when we're using this formula. So it's 0.1 by 60, which is 6, right? And that is 6 coulombs, right? So this is the amount of charge that flew through the copper wire, right? The next part is asking, determine how much charge goes through the simple cell in 60 seconds. So they want to know what is the charge that flows through the simple cell in 60 seconds. Now if we look at the circuit here, what type of circuit is that? Is it a series or is it a parallel circuit? Is that a series circuit or a parallel circuit? Right, so seeing everybody saying series, that is correct. So if it's a series circuit, it means that whatever charge, so the charge that you just got flowing through the copper wire, You got 6 coulombs, which means that same charge is going to flow through the circuit as well. So the answer is 6 coulombs, right? So there's no calculation there. It has to do with the fact that you are dealing with a series circuit. Okay? Now let's move on to this one here. So identify the type of current, which is AC or DC, right? Which generated the specific waveforms A, B, and C shown, right? Now, you all need to know the difference between AC and DC. So with respect to DC, the current flows in one direction only. So the current flows in one direction. And in the case of AC, the current reverses direction regularly with time. Right? So that's the difference between AC and DC. So in the case of E, can you all tell me what type of current is E? So what type of current would you say is? So Kendall is saying A is DC. John is saying, okay. Alright, so when you have a graph and you're looking for DC, we are looking to make sure that the graph does not go below my time axis, right? So type A is actually DC, right? This is a direct current. It is not AC, right? What about B? Right, so see Teresa and Kendall saying DC. Emily is also saying DC. That is correct. So this here is a direct current, right? And the last one, what is the last one? Xavier saying DC. So the last one is actually an AC. That's an alternating current, right? So the last one is an AC. So direct current flows in one direction only. So look at this. For this DC here, the graph is actually above my time axis. For this one here, it's also above my time axis. But the last one, C, we realize we're going above, below, above, below. So therefore it has to be AC, right? So the last part now, they want us to calculate the period and the frequency of the waveform. Period is the time for one oscillation. So I want somebody to tell me what is the period of this oscillation. So I've seen Emily saying 0.2, Kendall saying 0.3, Joshua saying 0.3. Alright, so your period is the time taken for one oscillation, right? So the time taken for one oscillation is this. It's going from here. This is one oscillation, one crest, one trough, right? So my time there is actually 0.20 seconds. That's my period, right? My period is the time for one oscillation, which is simply one crest and one trough. All right. Now the next part, now they want us to find the frequency of the wave, right? So frequency, right? You all need to know this. Frequency is 1 over my period, which is 1 over 0.20. Right? So 1 divided by 0.2, which is equal to 5, and my unit for frequency is hertz. Alright, so a question like this is probably about 4 marks. So the period, you read off that from the graph, and the frequency is simply 1 over my period, which is 1 over 0.2. When you get a question like this, pay attention to my time axis. Right? Time must always be in seconds. If they give us the time in milliseconds, please convert that into seconds, because when you work out the frequency, you're going to get an incorrect frequency. Right? So I only have a few minutes again. Let me see if I could start number 4 at least. Right? So they said Aaron, a Form 5 physics student, has available to him a bright filament lamp light in a ray box, an opaque screen, and 2 closely spaced narrow slits, and a large white screen. Describe how you would set up the apparatus to be able to observe an interference pattern of light and dark bands on a white screen, and briefly explain why this pattern forms. Now you gotta be careful with questions like this. You see, this question is broad. How many marks did they give for this? Let me just check something here. So 6 marks for that question. So here's what you need to do. First thing you need to do is to draw a diagram, right? Because what you want to show here is interference. So you have a bright lamp inside a ray box. So what we should do first is we're going to draw our screen here. 2 slits. Alright. You're going to have your lamp inside your ray box. Alright, so you have your lamp inside here, right? And the ray box is going to have a hole here. So the ray box is going to do this. Alright, and then what's going to happen here on the screen? So this is my screen. Right? What you're going to have here is right, I kind of draw the screen a little too far apart there, but that's okay. Right, so in this region here, right, you're gonna get bright and dark fringes. Alright, so describe how you can set up. So basically you have your screen, you have your ray box here. Your ray box. This one here is your double slit. Right? Right, so look at carefully what they want, right? So describe how you would set up the apparatus to be able to observe interference. So the interference pattern is where we're seeing the bright and the dark fringes, right? And they said briefly explain why this pattern forms. Alright? So here's what we need to say. We need to say diffraction takes place at each of the slits. So we have diffraction taking place at the double slits. Alright, that's the first thing taking place. Alright, and what is going to happen there is that the waves now, the light waves, are going to overlap. So the waves overlap. Alright, now when the waves overlap now, what is going to happen is that you're going to get bright and dark fringes being produced. So what we're going to say now is at the bright fringe, right, we're going to have constructive interference. So in order to explain constructive interference, what is happening is that you have a crest coinciding with a crest. So if this is A, the amplitude of that crest, what is going to happen is that you're going to get twice the amplitude. So this is 2A. So this is what is happening at constructive interference. Now just for putting this piece here, you might get about 2 marks for this. So a bright fringe occurs where we have constructive interference. We have 2 crests coinciding, and therefore the resultant amplitude is twice as large. Then we need to explain why we get a dark fringe. So we get a dark fringe when we have destructive interference. Alright, in which case what is happening is that crest is coinciding with a trough. Right? And what is going to happen is that the resultant amplitude is 0. So we have destructive interference taking place at a dark fringe. Alright? So please, because this question is very loaded, you need to be clear in terms of how you're explaining your answer. So in the Young's double slit experiment, as the light travels towards the double slit, diffraction of light takes place after the slits, right? Because the light waves are being diffracted, they tend to overlap. Now when they overlap, we're going to have interference taking place. But we have 2 kinds of interference. We have constructive interference and we have destructive interference. With respect to constructive interference, we have crest of waves coinciding. If crest of waves coincide, you're going to get twice the amplitude, right? And that is why we get in a bright fringe. But there are also areas where we have destructive interference taking place. We have a crest coinciding with a trough, and what happens is that the resultant amplitude is 0, and that is why we get in a dark fringe. Alright, so that is how we explain interference. So make sure you know the experiment, how to describe it, and how to explain the experiment. Alright, so I'm gonna pause there for today. Right, I hope you all had a good session. We will be coming back, continuing with this next week. All right, so we have chemistry taking place at 12:30. All right, guys, hope everybody okay. Hope the session was productive. All right, so I'm gonna stop streaming there now. All right.